Good morning, everyone. My name is Kaiwen Jiang. I'm currently a PhD student in mechanical engineering at the University of Birmingham. And today I would like to share with you a part of my work that was doing together with Chuxuan, an undergraduate student when he participated in this work, and Professor Pham, our supervisor. The title of my presentation is a comparison study between manual and robotic disassembly sequence planning using the in-house discrete bits algorithm. I know this is a bit long, but I can split it for you. So this work is around the disassembly sequence planning problem in the remanufacturing area. And with the increasing degree of automation, we want to compare the result between manually disassembly and robotic disassembly. And for relating to our topics today, the enhanced discrete bits algorithm is what we use to implement in the robotic disassembly sequence planning. Okay, so this is the content that I would like to cover in today. So firstly, for those BA users, if you are not familiar with the disassembly, I hope to explain a few definitions and application questions for you. And then secondly, I want to introduce you about this work and the model that we used an electric vehicle battery as our case study. And then thirdly, for those who are working with continuous problem or not familiar with the enhanced discrete version of this algorithm, I would like to show you a bit details of it. And then I want to present to you our results and finally close with some conclusions. So manually operations is a common thing in the industry now. And here are some characteristics of the manual disassembly, such as based on the manual operations, they are hand tools assisted. They are highly relied on the human operators and affected by the labor costs. Also, they generally performed in end-of-life product circumstances. And due to the complexities of disassembly process, the jobs are always finished by handwork now. But with the assembly processes of industrial products are seen to be done automatically, mechanical engineers are encouraged now to give more effort on automation technologies for the application of disassembly. So here we also give a few points to summarize the potential of automated and robotic disassembly. And then this is a comparison between the manual and the robotic disassembly done by Chuxuan. In the two-column table, he listed more characteristics of the choices. So our research question is to solve the sequence planning problem in the disassembly. And I here give you two of the problem descriptions that I'm getting from the literatures. So one of it is before the execution of the disassembly process, disassembly sequence planning, which is to find the optimal disassembly sequence, helps to improve the disassembly efficiency. Well, in another word, in this work, we focus on the computer-aided design-based model using the total disassembly time as our single objective function fitness and to solve the DSP problem, especially the RDSP. So this is the details and relating information of our case study, the EV battery. We split the components as 3 stages, stage 1, stage 2, and stage 3. And in every stage, we counted the number of each component type. So you can also see that there are 2 lab photos of our real battery here, this one and this one. And here is a typical manually screw and fastening work that is carrying on. And so for the disassembly time measurement, this is how we collected the data source. We arranged 3 people who have different levels of skills on disassembly operations. They are skilled, semi-skilled, and unskilled. So these 2 people here, 2 gentlemen here, they are skilled operators, and I am the semi-skilled operator, and Chuxuan was the unskilled operator. And then the following is our disassembly sequence that used in the lab. Well, finally, talking about the big part of today, the BIS algorithm. So in our robotic disassembly sequence planning work, as it is a BIS algorithm application, we didn't propose a new version of BIS algorithm, but to implement an enhanced discrete version of BIS algorithm, which was proposed by Dr. Jiang Liu and his co-authors in 2018. So here is the algorithm structure of his enhanced discrete BIS algorithm. And in the structure, he used the swap and insert and mutate these three search strategies as the local search. And then in the global search, he used the random search strategies. So we designed the parameter sightings by firstly following what Dr. Jiang Liu said in his two published work here at the bottom, of the number of selected sites as 4, this column, and elite site as 1, this second column, and selected Bs as 1, and also elite B as 2. And to test the different number of score Bs with 10, 40, and 80 here in the yellow, green, and light red. And also we tested with different max iterations number with 200, 600, and 1,000. So totally here we got 9 combinations. And then for the DSP problem related inputs, we gathered and input the right set following informations as the problem information. So we involved the disassembly basic time, we involved the disassembly distance, also 2 penalty times, which are direction changing and tool changing of the robot. So here's the result that we have got. We run the 9 combinations for each of the 3 stages and recorded their fitness values. We recorded 3 circumstances in each combination: the local best fitness value in score Bs as the blue columns here, and the local fitness value at the first iteration as the orange column here, and also the global best fitness value in the end as the gray column. So what we want to do is to deeply investigate how the BIS algorithm work when solving the RDSP problem. And to what extent can we amend the score BIS initialization method or the strategies of either the local search or the global search mechanisms, which can make the algorithm more efficiently when solving the problem. So back to this working today, these are the best results of disassembly times at each stage that I highlighted here with the purple color. So for calculating a total disassembly time for RDSP, we selected the best result at each stage and give them a summation. So you can see from here, from 3 different stages, the total using time is 1,259.54 seconds, which is around 20.9 minutes. And while for the manual disassembly process, we follow the way to gather the human operators disassembly time cost, and also we did a summation here. So the total time here is around 13.46 minutes. Well, the differences between this time and the previous RDSP time is that for humans, we didn't count in the human working or relaxing time in between each task, but human would do that when they doing the work. And so I think it is something worth to do if this comparison work is interested to be continued, that we would add the time of the human using in between the tasks into this total disassembly time cost. So as the total disassembly time is fairly close to each other between the RDSP and the MDSP, so why do we not choose robotics but human, right? And also from the BIS algorithm side, I would also like to show you the computational time that we use to run at each disassembly stage. So you can see that the more max iterations, the more computational time are consumed. And with more numbers of score Bs, the disparity of the results has larger gaps. So you can see the disparity gaps between here is smaller than the gaps between here, because they are using 10 score base numbers here, but 80 score base numbers here. Well, there are more interesting results I have recorded during the experiments, but however, due to today's time limitation, I wasn't able to squeeze all of them here, but hopefully I could analyze and show them to you in the coming paper format. And so from the BEAS algorithm side, I would like to say that parameter tuning is one of the critical and time-consuming steps in multi-heuristic algorithms. So I borrowed this sentence from Natalia, who I also participated this work in this parameter tuning work for solving the traveling salesman problem, which is also another combinatorial problem. So if you are interested, you can please feel free to read it after this event. And so also there is one point that I really want to call for your attentions is here. So which is the trade-in and trade-off issue. So I know that many of us, the BA users, that we want to pursue a very best result of BEAS algorithm to compare with the other meta-heuristics. And this is good, we should. But as it is said by our first presenter, the professor, there is a no free lunch theorem. So when we want to implement an algorithm into a real world like industrial problem, shall we or can we back off something, or and what content shall we give up or give away to it? So that's one of the questions that I'm interested when I using the BEAS algorithm, and I hope it may be of your interest too. So that's all for me today, and thanks very much for your listening.